when it comes to line integrals, this is the most important thing that you have to remember, that whenever you're integrating by something, divide by dt and multiply by dt. Okay. So divide by dt and multiply by dt. Okay, so let's see how we can solve this. First, you need to parameterize the path. So you have to write down C1 as a curve. Yeah.
I thought you interrupted me, yeah.
It's okay.
I will.
I'll edit it. Yeah. Oh. You did a good job. No, take your exam. Oh. I meant this exam, not. You're one of the 4 people who got 90 and above.
Hey, congrats.
People are copying down anyways. Okay. Yeah, I need you to focus, so let me wait until you copy it down. Okay, ready? All right. Okay, so in order to calculate these intervals, you need to parameterize these paths C1 and C2. Let's start with C1. What do I mean by parameterization? I mean, I need a function, a vector valued function, which means I need the x coordinate and the y coordinate, where at each time t, you imagine a particle moving over this path, where when t is 0, you're here, and when t is 1, you're here. Something like that, or t is something. And one quick answer is you want cosine t and sine t, because what do we know about cosine t, sine t? They're on the unit circle, right? So unit circle is smaller, it's radius 1, but it does start at this point, go circular, and at t equals to pi, you arrive at the other side, right? So this almost does it. What else do you need to do?
Length.
You should, huh?
Length.
Yeah, you make it bigger, right? So what do I do? Multiply by 3. And C1 will be parameterized by this one, where t is between 0 to pi. Good? All right. Okay. So now let's try to calculate what this is. So integral of C1 f dot dr is, well, f is negative y comma x. And this dot here is not multiplication, it's a dot product, okay? That's important. I'm writing a dot product. And I did explain why we're doing dot product when we do the line integral. It comes from the fact that in some contexts, this calculates the work done by some electric field or magnetic field, whatever, to a particle that's moving through that field. Okay, so the particle may gain energy or lose energy depending on this value. If this value becomes positive, then there's work done to it, so the kinetic energy increases. So when it as it goes through, the particle will speed up, and if it's negative, then the kinetic energy will decrease, so it's going to slow down or something like that. Okay. All right. So you have this, and then as I said, you should be dividing by dt and multiply by dt. The most important trick in calculating line intervals. And then because t goes from 0 to pi, so as this path, so just to give you an idea of what's going on is like, I took some time to draw this vector field last time, right? It was like when at 1, 1, the vector field is pointing that way. So it's a vector field that's something like rotating. Something like that. It's like something that rotates this way. And I was trying to explain, like, imagine that you had a coffee mug and then you're using a spoon to make it rotate in certain directions. It's like that. So fluid's going that way. And so that's happening. And the further you are, you have a bigger vector field. And then you're trying to go through this path C1, and at each point what you're doing is you're taking the dr, which is the small increment of this path. So dr means, because r is the position, dr is the small displacement of this particle. Okay, so as it goes, it's doing a dot product with the vector that's also going in somewhat of a similar direction. And you're doing a dot product, you're doing the multiplication, and then you're adding it over the entire path C1. That's what we're calculating, okay? And because it's impossible to calculate this as it is, you have to convert this into a parametrized form. And to compute it with the parametrization, the trick is always divide by dt and multiply by dt. That's what I mean, okay? All right, so what is dr dt? dr dt means you're differentiating, right?
Mm-hmm.
So what is dr dt? Negative
Sine
3 sine t, 3
cos.
cosine t. So that's going to be now, t goes from 0 to pi. That's going to be from 0 to pi of negative y comma x dotted with negative 3 sine t comma 3 cosine t dt. Now, if you have this picture, you also realize that, see, RT is the position of the particle, right? And when you want to calculate f dot dr, you have to evaluate the f at the location RT. Okay, so this one here really means you're trying to calculate the vector field at RT. So even though I wrote down negative y comma x, that's really evaluated here. So when you evaluate f of RT, this is a composition of functions, right? This arrow with the letter R, that's what I meant. Looked like an F. When you have a composition of RT, what I mean is I'm plugging this into the function f. F takes in x and y and produces that, right? So let's see what that is. See, when you plug this into here, 3 cosine t goes into x and 3 sine t goes into y. Is that good? Right, so this is like the x and that's y. That's what's happening. And therefore, FRT is going to be f of 3 cosine t, comma 3 sine t. And because whatever you plug in, f is like switch the two around and put a minus on the first one. So that's going to be like negative 3 sine t, comma 3 cosine t. Okay, that's what's going to happen. And therefore, if I continue the calculation, it'll be 0 to pi. See, it's negative y, but y is, again, 3 sine t. And x is 3 cosine t. When you do the dot product of these two, yeah, it's just a coincidence that they end up being the same. Usually they're not. Okay. When you multiply, dot product is component-wise multiplication you add, right? So you end up with 9 sine squared of t. 3 times 3 is 9. Cosine times cosine is cosine squared. That's what you get from 0 to pi dt. And that's going to give you sine squared plus cosine squared is 1, right? Because this plus this is 1. If you factor the 9 out, you just end up with 9 times 1, which is 9. That's 9t, and you plug in pi and 0, you get 9 pi as a result. That's the result of this first sentence. Any questions so far? Yeah.
So we're finding like the distance between A and B using both paths.
No, we are finding the amount of work done by the vector field if the particle is moving in this trajectory.
Okay.
So, like, imagine that there's some moving particle, some this is like some gravity field and some strange gravity field, and then you're a spaceship on here. Then, let's say you're taking this path from point A to point B. Yeah. And then the work is force times distance. Well, it's really 4 times distance times cosine, which is really the dot product. So it's the dot product between the force and the change of the displacement, right? And you add them up, you get the total thing. But think about it this way. Like, do you see that the actual vector field and the direction vector are kind of in the same direction? Yeah. Actually, if you drew more accurate things, you'll see that they're actually parallel. It's exactly the same thing. So that means that as you go this way, it's going to speed up. And the kinetic energy will be bigger because it speeds up. Like, kinetic energy is 1/2 mass times velocity squared, right? So you do see that there's an increase in the kinetic energy by 9 pi. That's what it means. But even before doing the calculation, what if we took this path? What's going to happen if we go this way?
Slow decreases.
It'll be slowing down because you're going the opposite direction. The vector field the force field is working against you, right? Yeah. So definitely, even if you start with a very fast initial velocity, the countering thing is going to make it slow down, so you have a negative value in the work done by the vector field. Okay. So kinetic energy will go down. In other words, for this second value, the answer better be negative, because if it's positive, something's not right. Is that good? All right. Okay. So let's now try to do the second one. Now this is more challenging. How are you going to parametrize this? And let me give you some options. So one option is just see that every point on top, if you just change the y coordinate is negative, you get here, right? So one option is 3 cosine t comma 3 sine t was C1, right? But just put a minus on the y-axis, and that's it. Okay. Then it's easy. T goes between 0 to 2 pi. 0 to pi, still. And indeed, that will be how it's going to be.
I have a question.
Yes.
Would it be the same thing if you did 3 cos t negative 3, sorry, just 3 sine t, and you did 0 to negative pi?
Right. So okay. Yeah, that was my next point. Okay, so another way to do this is, well, aren't you, like, 3 cosine t, 3 sine t is going to be going on this circle anyways. But if you think about it, this is the case when t is 0, and this is the case when t is negative pi, right? So if you go from 0 to negative pi, so if t goes from 0 to negative pi, then that's another way to do the same thing. Okay, so that's another one. We'll just stick to this one, but I just want to give you some other options. There are infinitely many ways to do the same parametrization, so you have to be able to come up with these things. It's not so easy. Here's another way to do it. If you do, here's angle pi, and here's 2 pi, right? If you do angle 2 pi to 2 pi, so if t goes from pi to 2 pi, you get something like C2, except the orientation is backwards, right? Yeah. So what you can do is you can say minus C2 is parametrized by 3 cosine t, 3 sine t, with t between pi to 2 pi. Okay? And what that means is that you can still use this to do this calculation, except that you just have to put the minus. So C2 f dot dr is going to be pi to 2 pi, but because we're using the negative of the parametrization, you just need to put a minus there, okay? With the f dot dr dt, dr over dt, where r is this one. Okay? That's still another possibility. Okay? So I'm only going to do the first one, but please, when you're reviewing this later, then you should really try to do this one and get that all 3 different parameterizations give you the same exact answer. Okay? Yeah. And then there's like plenty more. Like for example, you could also do, instead of cosine t, you can do cosine pi t and divide the t by t going from 1 to 2. That's another possibility. So there's so many different possibilities. They all should be leading to the same answer, because the integral shouldn't depend on the parametrization. For C2, now we are using this one. So again, you go from 0 to pi, and then f evaluated at here is what we need. 3 cosine t, negative 3 sine t, and then dotted with 3 cosine t, comma negative 3 sine t. Oh, no, that's not right. What am I saying? Sorry. We should be doing dr dt, dr over dt. Yeah, this trick, divide by dt and multiply by dt, okay? So we should do that. And then, what is this? This is our vector field switches x and y and puts a negative in front. So this part is going to give us 3 cosine t is now going to be the y coordinate. And this becomes the x coordinate, but you have to negate that, so that's going to be 3 sine t, like this. And then dr dt, what's that? You have to differentiate this, so you get negative 3 sine t, comma negative 3 cosine t dt. And this just ends up being negative 9 dt, so that's going to be negative 9 pi. The rest of the calculation is pretty much the same thing as the previous one, so I'm just skipping steps there. I really want you to mainly focus on the parameterization and this trick, dividing by dt and multiply by dt. That's the important.